Welcome to the first lecture of week 8 of the course Introduction to General Relativity. This part of the course is called Mathematical Preliminaries Part 2. And we focus on learning Riemannian geometry, or the essential tools from Riemannian geometry, concepts such as metric, connection, curvature, geodesic equation, geodesic deviation equations, which are essential for operating in general relativity. The main references for this entire part, mind you, I'm not giving you references for this lecture, but this whole part overall are as follows. The main reference I'll be using is Nakahara's textbook. I'm going to cover most of chapter 7 with some exceptions. Here the sections are indicated. And also it is important to note that I'm using the second edition of the book. Carroll's lecture notes, second chapter, 8 pages, as well as entire chapter 3. And Hawking analysis textbook, second chapter, sections 2.5 to 2.7, cover a similar amount of material and can be considered as alternative references for this part. As usual, the lecture notes will be posted on the NPTEL-NOC website. You can refer to them as well. And finally, for those who are looking for a little bit of mathematical depth and rigor, can refer to Lee's excellent text on Riemannian geometry, which is a mathematics text at the graduate level. All right, for background, I'm going to assume familiarity with the idea of general coordinate transformations, which in the differential geometry language can mean either of the two things. It could mean inter-child transition functions, which is, as I have mentioned, a passive form, or it could mean diffeomorphisms, which is the active form. I'm also going to assume familiarity with tensor index manipulations and invariant tensors from special relativity. I'm also going to assume knowledge of identities relating to determinants. All right, let's look at the agenda for today's lecture. Our aim is to become familiar with the concept of a Riemannian manifold and the associated notion of a Riemannian or pseudo-Riemannian metric. We will learn about the inverse metric and the raising and lowering operation for tensor indices, something which you are already familiar from special relativity. And more or less, this idea will go forward without much modification, without drastic modification. Then we will revisit the notion of an invariant tensor for a general manifold, Riemannian manifold. And here it will turn out that the Levi-Civita, which was a tensor in special relativity, is not a tensor under general coordinate transformations. In fact, it is a symbol. So a symbol is an indexed object, an object which has indices, but which is not transformed like components of a tensor under general coordinate transformations. Okay, so these kind of objects which have indices that fail to transform like components of a tensor are called symbols in general relativity. So the Levi-Civita will turn out to be a symbol. Then we will learn about how the metric determinant transforms in general coordinate transformation. There is a little bit of ambiguity here. I'm using little g to denote the metric as well as the determinant of the metric as well. I hope it will be clear from the context which one I'm referring to. Once we are done looking at the transformation of the metric, it will turn out that the Levi-Civita can be converted into a tensor after all. Okay, so we will learn about how to construct this Levi-Civita tensor from the metric determinant and the Levi-Civita symbol. Then we will look at the invariant volume form. This is a very special object. It's a volume element which remains invariant in general coordinate transformation and plays a very important role in general relativity. Then we're going to learn about the concept of tensor densities. Again, there is a special class of symbols, that is, objects which have indices. These are a special class which have a very special transformation rule, as you will see. And the important thing about tensor densities is that it is possible to convert a tensor density into a tensor. Okay, and we will see what is the recipe to construct tensors out of tensor densities. and we will start here. Okay, let me start with the definition of a Riemannian manifold and the Riemannian metric. But before that, a little bit of motivation that the curved spacetime of general relativity, which is given by this line element. So most of you by now have understood that turning on gravitational field, what it does is that the Minkowski metric of spacetime gets distorted. So when you turn on the gravitational field, the Minkowski metric gets distorted by the Fierce-Pauli field, or better to say, contributions from the Fierce-Pauli field. Those higher order contributions, which I'm not writing, quadratic, cubic, and so on and so forth. But the bottom line is that once we turn on gravitational fields, the metric fails to remain Minkowski, and one has to replace it by G-nu, which is a space-time dependent function. So it's a function of space-time location. So this kind of space-time is called closed space-time or warp space-time. And the mathematical model for warp space-time is a Riemannian manifold. That's why we need to learn this. So a Riemannian manifold is a pair, M comma G, as you can see, M comma G here, which consists of a differential manifold M and rank 0,2 tensor field little g, which is called the Riemannian metric. It satisfies certain properties, which I'm coming to in a second. But the idea is that a Riemannian manifold is a manifold on which a metric is specified. Okay, so the metric, because it's a 0,2 rank tensor field, it will have components and bases. I'm writing the metric in coordinate basis, in which, because it's a 0,2 rank field, the coordinate basis will be a direct product of two one-form basis elements, and then this real number g sub the nu of x is the component of the metric. All right. To reduce clutter of notation, I did not specify the dimension of the manifold, but of course you can assume this is the n-dimensional manifold. Okay, m raised to the n. Now, because we have specified tensor rank 0,2 tensor field, it can be used to define inner products of vectors. Okay, consider u and v, which are two vectors, that is, they're elements of the tangent space. Then I can define an inner product of u and v, which is given by this notation, g of u comma v, and this is equal to the product of the components, and the indices are contracted. As you can see, mu is contracted here, mu is contracted there. Okay, so as a result of the metric, now it has become possible to define inner products of vectors and norms, of course. Now, another thing which happens is that because of the metric, one can define, introduce an infinitesimal distance between points. Okay, consider 2 points with coordinates x and x plus dx. So let me just draw a little bit. 2 points, whose coordinates differ by infinitesimal amount. Okay, so this is a coordinate patch in which both points lie, and so the 2 points, their coordinates differ by infinitesimal amounts. Now, I can always define a displacement vector, which I've defined here, dx, which is equal proportional. The components are dx, and the basis element is the same as the tangent space. I can define this displacement vector, and because g can be used to define the products and norms, I can ask what is the norm of this displacement vector. So that will obviously, using this formula, turn out to be this. This gives you a notion of a distance between 2 points. Okay, so the metric allows you to define, to introduce a notion of a distance between two points. Okay, so there are some restrictions on the metric tensor for it to qualify to be a Riemannian metric, and these two properties are symmetry and non-degeneracy. Okay, so symmetry first. The symmetry means the inner product is insensitive to the order in which I insert the vectors u and v. So g of u and v is equal to g of v comma u. In terms of the components of the metric, this means that g mu of x is equal to g nu of x. Okay, so under the swap of the components, the value of the metric remains the same. So if I introduce a matrix which is populated by the components of the metric, so this is a matrix because I'm making square brackets around it, in which the newest row element and the newest column element is given by G mu. So it's a matrix whose newest row, newest column element is G mu. So then this first condition means this is a symmetric tensor, so its transpose will be the same as itself. And the second condition is non-degeneracy, which tells you that if the inner product of u, of a vector u, with any vector, any and all vector v, vanishes, the inner product of u with any vector v, actually every vector v vanishes, then there is no other solution other than the fact that u is the null vector. Remember, null vector is a vector whose components are all 0 in any basis element, in any basis. So what does that mean? So let me just write down G mu equals 0 for all v. That means this cannot be 0 for v, so we can remove the v. That means G mu equals to 0. That means u is an eigenvector of the matrix G with an eigenvalue 0. So what it tells you, non-degeneracy condition tells you that the metric cannot have an eigenvector with eigenvalue 0. Okay, so the metric cannot have 0 eigenvalues. Okay, this is good because then this matrix becomes invertible. Okay, so invertible G. Okay, so invertibility and transpose the symmetry, these are conditions on the metric tensor. Now G can, we ruled out G having 0 eigenvalues, but G can have both positive and negative eigenvalues. If it has both positive and negative eigenvalues, those metrics or manifolds are called pseudo-Riemannian. If it's purely positive, then we call them Riemannian manifolds. On the other hand, in the more general case, when you have both positive and negative eigenvalues of the metric, we call those metrics or manifolds pseudo-Riemannian. In particular, if there's only one negative eigenvalue, we will call that a Lorentzian manifold. Okay. So, in general, we introduce the notion of a signature which captures the number of positive and negative eigenvalues. So, if the signature is p comma q, that means it has p, the metric has p positive eigenvalues and q negative eigenvalues. So, in our course, mostly we will use signature 3 comma 1. So, there will be 3 positive eigenvalues and 1 negative eigenvalue most of the time. But in general, in string and supergravity, one can consider more general p comma q signature manifolds. So we should keep our mind a little bit open. Now, since G has positive and negative eigenvalues, ds squared, the distance between two infinitesimally close points, is actually indefinite. It can be positive, negative, or 0. So space-time intervals can be space-like depending on whether this line element is positive, or time-like if the line element is negative, or light-like if the line element is 0. Similarly, because the metric is indefinite, it can have positive and negative eigenvalues. Vector norms are also indefinite. We can define space-like vectors for which the norm is positive. We can define time-like vectors for which the vector norm is negative. Actually, I'm using norm, but what I actually mean is norm squared. And like-like vector for which the norm squared is 0. because the metric is a tensor, we define the metric as a tensor, it will obey the appropriate tensor transformation law. Because it has two lower indices, we will have to put two factors of the inverse Jacobian. So this is transformation law under general coordinate transformation, x going to x prime, which is a function of x. Again, as I said, I'm covering both cases, passive as well as active. The passive case is when we're looking at transformation when we go from one chart to the other, in which this point was given by coordinate x, while in the other chart, the same point is given by coordinate x prime, and x prime is a smooth function of x. So in such a case, the metric at this point in two-coordinate system, they're related by the transformation law. On the other hand, when we consider diffeomorphisms, x and x prime are two different points. And then there is a smooth map which takes me from, or a diffeomorphism which relates x to x prime. As you know, a diffeomorphism is an invertible smooth map with the inverse is smooth as well. So I can always define the inverse map, which takes x prime to x, so x prime becomes a function of x. X becomes a function of x. This is the inverse map. This is the direct map, and this is the inverse map. So under this inverse map, we can define a pullback, which will take the metric here at x to the metric to some pullback metric at this point x prime, which is also given by the same formula. Okay, and one can check easily that the space-time interval as a result of this transformation law will remain invariant. Okay, so it's staying in both forms. Okay, so one exercise I will suggest is to use this transformation law to find out what is the metric of the Euclidean plane in polar coordinates. Okay, so you start from the metric of the Euclidean plane in Cartesian coordinates, in which is the x squared plus the y squared. Very simple. And then use the transformation from Cartesian to plane polar coordinates to write down the metric in plane polar coordinates, which will turn out to be something like this. We'll do this as a homework. Okay, so just use this transformation law to work out what are the components. Okay. All right. Next, we move on to the notion of an inverse metric. So the non-degeneracy of the metric allows us to define the inverse metric, which would be a rank 2, 0 tensor, so with upper indices. So we have something with upper indices, a component. And of course, because it's 2, 0, the basis will be a direct product of the basis of two coordinate partials. So I'm using coordinate basis, of course. We can use general basis. But in coordinate basis, it would look something like this. And the component, this real number, g superscript mu of x. And because it's the inverse metric, these components are defined by this condition. So as you can see, metrically, this is inverse. Matrix-wise, it is inverse. So G, the statement is of this form, G inverse G equals identity. Okay, so this is the definition. And what simply follows is that because G is symmetric and non-degenerate, so will be G inverse. The one thing I will caution is that I've claimed that the metric is non-degenerate. However, if you choose bad coordinates, then the metric can look degenerate. One example would be the plane polar coordinates, because in Cartesian coordinates, the metric of the Euclidean plane is the x squared plus the y squared. Sorry about that. So if I write down the metric as a matrix, this is diagonal 1, 1, this is V11, V2, 2, and then V1, 2, and 2, 1, and 0. So in Cartesian coordinate, the R2 metric is the diagonal from which we can see the diagonal eigenvalues of 1 and 1. So of course this is non-degenerate. On the other hand, if we write the same R2 in a different coordinate system, in polar coordinate system, in which it looks like dr squared plus r squared d theta squared, then the metric reads something like this, matrix form. It will be 1, 0, 0, r squared. So the eigenvalues are 1 and r squared. Then if r is equal to 0, then we have a 0 eigenvalue. So then it feels like plane polar coordinates, we have a metric which is degenerate, but this is not the right thing to do because at r equal to 0, the plane polar coordinates are not good. Theta is not defined at r equal to 0. So it's supposed to have a set of coordinates. So whenever, if we start with the non-degenerate metric, and if we do some coordinate transformation which leads to degeneracy of the metric, we say that coordinate system is not so good because the metric has turned degenerate. All right, contraction with G, a lowering of tensor indices. So this, I think you have some idea from special relativity. Here, just like in special relativity, the metric will convert tensor vector into a covector or a one form, and it is given by this formula. So if you contract G mu with this vector component, then you get something which has a lower index. So this is a one form, component of a one form. And you can repeat this process for a general PQ rank tensor. And if you contract it with G, you end up with getting the number of countervariant indices diminished by 1 and the number of covariant indices augmented by 1. Okay, so this is the formula. As you can see, I've taken G mu alpha n and contracted with some tensor which has another alpha n in the superscript. And then as a result, this defines a new tensor which has, instead of the alpha n, alpha sub n raised, you have some mu which is in the subscript. So its quantivariant rank got diminished and the covariant rank got augmented. Okay, and you can repeat the same thing, but with the G inverse. In that case, we have an operation which is called raising tensor indices. Now this will convert a covector into a vector, and this is the formula for that. As you can see, that you start with a covector, you contract with the inverse metric, and you end up getting something with an upper index, which is nothing but a vector. And you can repeat that same thing for a general P, Q rank tensor. Once you contract with the inverse metric, you end up getting another tensor, except its quantivariant rank is augmented by 1 and covariant rank is diminished by 1. So here is the formula for this. As you can see, I have a tensor and I've contracted with the inverse metric. So this index beta sub n, which is being contracted, will be removed on the right hand side, and instead you will have something which has an upper index mu on the right hand side. Okay, so this index got raised. The index beta n was raised and converted into a mu. All right. So let's revisit the notion of invariant tensors. So in Minkowski spacetime of special relativity, invariant tensors are invariant under Lorentz transformation. That is, their components remain the same in all Cartesian inertial frames. So you start with some Cartesian inertial frame, you do a Lorentz transformation, you think the tensor will change because the basis has changed, but it turns out that the components do not. So these kinds of tensors are called, as you know very well, invariant tensors. And there were 3 of them: the Kronecker delta, Minkowski metric, and the Levi-Civita. Okay, so let's take each one of them one by one. Now, Kronecker delta is still actually invariant tensor under general coordinate transformation, not just Lorentz transformation. And this is very easy to see. So we can write the Kronecker delta as this derivative of the prime coordinates, mu and nu. And unless mu is equal to mu, this is going to be 0. So this is Kronecker delta, of course. Now then, but the x prime mu under general coordinate transformations, x primes are smooth function of x's. So we can evaluate this determinant using chain rule, which we have done. So you can see chain rule here. And then the first one we keep as it is. The second one, this alpha, we relabel as beta. But to make the indices correct, we also contract with the Kronecker delta, so that this beta gets converted into alpha. And these were the same thing. Now, if we do this and we carefully look at what happened to the right hand, so what the right hand side looks like, it looks like the tensor transformation rule or a rank 1,1 tensor. Right? You have the component, and then we have two factors of the Jacobian. One factor of the Jacobian and the other factor of the inverse Jacobian, exactly the same. So this tells us that A, Kronecker delta transforms like a tensor, and B, it's an invariant tensor because the right hand side component is same as the left hand side component. Okay, so Kronecker delta survives being an invariant tensor when we go from special relativity to general relativity, that is going from simple Lorentz transformations to general coordinate transformations. And the metric tensor, unfortunately, is not going to be a tensor. We know this very well already because the components do change. We just saw in the example I gave you, in which you write the R2 metric in Cartesian coordinates, in which the components are these, G11 and G22 while G12 and G21 are 0. While in plane polar coordinates, G11 is 1, G22 is not 1, it is equal to R squared. So clearly G22 didn't remain the same, it changed. So the metric is manifestly not an invariant tensor. It is a tensor, it is just not an invariant tensor anymore. So we'll cross out from our list. And then the last thing to check is the Levi-Civita. Let's look at this. So this is, of course, I'm in 4 dimensions. I'm going to go in higher dimensions, but for the time being, let's consider 4 dimensions. So there are two associated questions. A, is it a tensor? And we should keep an open mind because it might not be. It will turn out it is not. And the second question is that if it is tensor, then is it invariant? Okay. So let's define the Levi-Civita symbol. Let's assume that it is not a tensor, and let's write it. Define it by this thing, indexed object, epsilon, curly epsilon actually. We will introduce two kinds of epsilons, or Levi-Civita. So this is the curly epsilon. So this epsilon is 1, or if I'm using indices 0 to n minus 1, then this is equal to 1, as it happens for a Lorentzian manifold, and this is more true for a Riemannian manifold. And complete antisymmetry, that is this epsilon, the curly epsilon with mu1 to mu(n) is plus 1 if it's an even permutation of 1 to n, and minus 1 if this mu1 to mu(n) is an odd permutation of 1 to n. Okay. So this is, now we have defined the Levi-Civita symbol, and now we have to check how does it transform. To see that, first we have to recall the definition of a determinant of n by n matrix. So n by n matrix, which is A, and its elements are mu, nu. The row index is upstairs, the column index is downstairs. So this is the definition of a determinant, or property of a determinant, that if you have the product of these n components of A, when contracted with the Levi-Civita, gives you the Levi-Civita times determinant. So the determinant I'm denoting by this absolute value or modulus sign. This actually means determinant. And then now I'm going to, for this A, there's the inverse Jacobian. So del x prime. Of course, you have to put indices, but I'm being a bit careless and have not indicated any indices. to reduce clutter of notation. So if A is the inverse Jacobian, then this identity gives this important result, as you can see. So we have Levi-Civitas on both sides, and some these are all lower indices, so we have inverse factors of powers of the inverse components of the inverse Jacobian, and then we have J sitting in front of it. So if the Levi-Civita was an invariant tensor or a tensor, we would just have these, okay, components of the inverse Jacobian. We would not have this Jacobian determinant appearing. Because the Jacobian determinant appears here, this is not the transformation rule for a tensor. So the Levi-Civita symbol is not a tensor. What it is, in fact, is a tensor density of rank 0, 4 and weight 1. I will explain what this is. But just remember the fact that it got disqualified from being a tensor because in addition to having components of the Jacobian, inverse Jacobian featuring in the transformation law, we also had the determinant of the Jacobian featuring. So that is not the transformation law for a tensor. So before I introduce tensor densities, I want to look at the transformation of the metric determinant, as I said in the introduction. So the determinant identity I'm going to use is for again an n by n matrix. Now this time it's a matrix in which the row and column indices are both upstairs. So mu is the row index and alpha is the column index. And the determinant satisfies this identity. That what we have is two Levi-Civita symbols, which are contracted with n number of components of A. And of course, we sum over all mu and all alpha, then we get this, okay, with an factorial in the denominator. Now, instead of a general matrix, I'm going to specialize to the inverse metric, which is given by G with upper indices. The inverse metric determinant, instead of putting absolute value sign, I'm just going to denote by G inverse. The G inverse means the inverse metric determinant. And then we have this identity here. So our question is, how does this transform under a general Fourier transformation? For that, we recall that the metric itself transforms like this, or the metric inverse transforms like this, with two powers of the Jacobian component. And this leads to the fact that the metric determinant transforms like this. So G prime is the metric determinant in the new coordinate system, G is the metric in the old metric determinant in the old coordinate system, and G prime is equal to the Jacobian determinant raised to the -2. Okay, so this is how it transforms. I'm skipping the derivation. You can always look at the notes that this is how the derivation works. You start with the definition of the inverse metric in different coordinates, inverse metric determinant in the prime coordinates, and use this formula, use this identity. And then in each of these G prime, you introduce the transformation rule. And then reassemble these with proper indices contracted to get this result. Okay, please look at the lecture notes when I've gone through the steps of the algebra. The bottom line is the metric determinant transforms like that. And if I take square root of both sides, we have this rule. So remember to put absolute value sign, because the metric determinant can be positive or negative because it has both positive and negative eigenvalues. If it has one negative eigenvalue, sometimes we write it in this way. So this is what you will find in most textbooks of general relativity, square root of minus G prime, because it has only one negative eigenvalue. So we're just putting it, the minus sign makes it positive, and then you can take a square root is equal to the inverse power of the Jacobian determinant, except you have to take the absolute value and then square root of minus G again. Okay. So now let me write side by side the transformation law for the Levi-Civita symbol, which was that it had all these powers of the inverse Jacobian components and the Jacobian determinant, which is what disqualified it from being a tensor. On the other hand, in square root of g, we have a power of j determinant inverse. So very easy to guess that if I construct something which is a product of these two, then the powers of j will cancel each other. Powers of determinant j will cancel each other. So define a Levi-Civita tensor. Actually, this is a pseudo tensor. I'll come to a point momentarily. What do I mean by that? Levi-Civita pseudo tensor, which is defined to be square root of minus g times the Levi-Civita symbol. So notice there are two different epsilons I'm using. One is the curly epsilon, which I have reserved for the Levi-Civita symbol, and there's the usual epsilon, which is the Levi-Civita pseudo tensor. And you can ask, what is the transformation law under general point transformation? It's very obvious that g prime and epsilon, it's obvious by taking a product of the two respective left-hand sides and two respective right-hand sides that the transformation rule looks something like this. So you can say, well, this is not a tensor because you have the sign of j appearing here. But that is not a big deal, especially for zero coordinate transformations. We do not reverse the handedness of the axis. For example, if we don't allow parity or time reversal, then this sign of the Jacobian will always be positive, and it will go away. Then we have something which is something like a tensor, because the transformation rule only involves powers of the inverse Jacobian components. So this has actually this is not rank 4 by mistake. This is rank n because I'm looking at n dimension. Okay. So now let's look at the invariant volume element. So volume element before x in 4 dimensions, you're already familiar with this, which is the wedge product of the one forms. Because in 4 dimensions you have 4 one forms. This is kind of unique. And we can generalize this in n-dimensional space-time, that is n-1 space and 1 time. The volume element is given by the n form, which is also unique. By this wedge product. Now the question is, how does this volume element transform under general coordinate transformation? Of course, you have to do that by looking at transformation of the one form and then performing the wedge operation. It turns out that the transformation rule actually, after doing all that, is very simple. It is just the same Jacobian rule which we use in multivariable calculus. The volume element in prime coordinate is equal to the Jacobian determinant times the volume element in the unprimed coordinate. Okay. So again, so the volume element is also not a tensor because it contains the factors of determinant of the Jacobian instead of just the Jacobian components. Okay. So in particular, this is a scalar density of weight 1. So it's scalar density because if we didn't have this factor of the Jacobian determinant, this would be a scalar because dnx prime will be equal to dnx. But that is ruined or spoiled because of the presence, due to the presence of this Jacobian determinant, and only unit 1 power 1 appears. That's why it's weight 1. Okay, we will explain that momentarily. So to get a invariant volume element or volume form, we define this combination again, just like for Levi-Civita. We define this square root of minus g times dnx. And as you can see, g will have transformation law for g will have this inverse of the Jacobian determinant. Transformation law for the volume will have one power, so they will cancel each other and you'll get some invariant volume element. Okay. So again, this is only invariant under proper general coordinate transformations, in which the Jacobian determinant has positive sign. Okay. the Jacobian or the transformation, the determinant has positive signs. Okay, that means we are ruling out things like parity and time reversal. All right. So the final slide, which is on the tensor densities of weight W. So it's an object which has indices. I'm using the Gothic alphabet for this. So instead of T, the Gothic T, this is the rank P comma Q because it has P upper indices and Q lower indices. And it qualifies to be called a tensor density instead of a tensor if its transformation rule involves W powers of the Jacobian determinant. Okay, in addition to the usual tensor stuff, so because it's rank P comma Q, you have P factors of the Jacobian matrix components, you have Q factors of the inverse Jacobian matrix components, and on top of that, we have W powers of the Jacobian determinant. Then we call this kind of an object which transforms like this under a general coordinate transformation a tensor density of weight W. Okay. And the good thing about tensor densities is that they're salvageable. One can construct a tensor out of them if you want. So the way to do this is to take the square root of the metric determinant or absolute value of the metric, raise it to the power of W, and multiply with the tensor density. The resulting object will not have, because we multiplied by these many factors of square root of G, which will give compensating factors of Jacobian determinant inverse, which will kill this. And as a result, the transformation law will start looking like this. The only thing that will survive is the sign of the Jacobian determinant raised to W powers. So W is even, this will always be positive, and it's a tensor. If W is odd, it will have a minus sign, so we will call those cases pseudo tensors because they are only tensors under transformation for which the Jacobian determinant is positive. All right, so let's look at the summary for today's lecture. First, we introduced the notion of a Riemannian metric and a Riemannian manifold. We then introduced the notion of an inverse metric, and we revisited this raising and lowering operation for tensor indices. We saw it's almost the same as what you had for special relativity, except the Minkowski metric is being replaced by the Riemannian metric. And then we revisited the notion of invariant tensor, and we found that the Levi-Civita sees this to be a tensor. In fact, it is a symbol, which we denote by this curly epsilon. Then we looked at the general coordinate transformation of the metric determinant. I've written it here. So the metric determinant doesn't transform like a tensor either. In fact, it's a scalar density of weight minus 2. And then the Levi-Civita symbol and the metric determinant can be combined together to revive the Levi-Civita tensor, which we denote by this epsilon, mu, etc., defined by the product of square root of the metric determinant or minus metric determinant with the Levi-Civita symbol. And similarly, we will define an elementary volume element or elementary volume form, which is given by the square root of G times the usual volume element. This is invariant on the general coordinate transformations, so it's a scalar. Finally, we define what tensor densities are and how to convert them into pseudo tensors by multiplying them with appropriate factors of square root of minus G. And that's where we will stop today. Up next is some physics. We will look at how point particles move on the Riemannian manifold. This will lead to the geodesic equation, which are shortest or extremal curves. And then we will look at the notion of symmetries of metric or isometries. This will allow us to introduce the notion of scaling vectors and conserve charges in general relativity. So we will stop here. Thank you very much. See you next time.